will speak also about mixture designs and trying to reconcile mixture and factorial designs, because basically we always say food can be modeled very easily by saying we process a mixture of ingredients. So we have to put the two things together very often as soon as we cook or do something with and not just mix the ingredients. So this is a method that we use quite a lot within the group, and that's also the reason why all these people from the group are co-authors of that. Suppose I just introduced that with an example. It's infant cereal. It's a Nestum. Nestum, this brand here is basically wheat cereal, and it's with a little bit of sugar. And if I'm looking at the process of this, again, very simplified, I put the wheat and the sugar together, I soak it, I cook it, I dry it. And if I want to optimize this process, and I look at all of it just at two levels, just short, long for soaking, mild, strong for cooking, and mild, strong for drying, and I represent what I would do in terms of experimental design, is just 3 variables, 2 levels each, so it's just this cube with 8 trials. If 8 trials I'm not able to do, and this is often the case in the problems that we have, because just one of these trials, perhaps not for infant cereals, but for other products, if it costs 10, 15,000 Swiss francs to make just one trial, then reducing from 8 to 4 is sometimes extremely important. And that's where we would go with a fractional factorial design with just 4 experiments. Now suppose that we have ingredients. So we have not only the process, we have also ingredients. So we move from something where we have just wheat, and we can exchange part of this wheat by sucrose between 0 and 10%, glucose 0, 10%, fructose 0, 10%. Again, if I'm looking only at the ingredients, I would end up with 8 trials. Again, if I don't want to make 8 trials, I can do just a fraction of it with 4 trials. There was a nice book in '99 by Mr. Barton where he was making a lot of this type of drawings, where you can see that if I want to make all these ingredient mixes at each process setting, then it makes me 2,3 times 2,3 equals 2,6 is 64 experiments. Again, if I don't have the money for that, I can do something easier, and I go with 16 experiments. And this is the logic of saying, okay, I have process, I have ingredients, and I cross the 2 process, cross ingredients. Much more logical would be, in fact, to do something where we do the 2 things together. And a little bit in the logic already of what Michel was presenting, if you, instead of choosing just to have 4 out of the 8 process points, if you choose well in your fractional factorial design your columns of your your design, then you can first of all have each process parameter each process setting that is given once, even with only 8 trials, and you can also arrange that you have each ingredient setting that is once there. Just by selecting nicely my column of my orthogonal array, just by saying that these 3 columns have a strength of 3, these 3 columns have a strength of 3, which would not have been the case if I would have selected AB, AC, and BC, for example, where I would have just a strength of 2, and where I would have not 8 trials in this red cube, basically, but only 4. So here in the logic, a little bit of space filling. I'm making every process condition once, every ingredient condition once, and this with only 8 trials, and just by selecting intelligently the columns of my orthogonal array. Basically, that's the first thing. For sure, that's not at all what we are doing, because if we would do that, that would mean that we have some trials where we have 0 sugar, and another trial where we have 30% of sugar, and that's certainly not what we are doing. And that's exactly what Michel was just presenting, is that in terms of sugar, we say that, yes, sucrose can move from 0 to 10, glucose from 0 to 10 and fructose from 0 to 10, but the sum of it has to be 10 basically. And I show the same figures than Michel was showing. So we are with a Simplex lattice design, if we are in the logic of what we have here. I just added one center node, 2 center points here. I will show you why I added 2 center points here. And if I make here, I have also a Simplex lattice design with 1 center point here. And yes, I cite the same people than Michel, so that's my friend Cornell. And then, if we would do process time mixture, we would end up again with 64 trials here or 16 trials here. Or if I use intelligently the path that I had before and I project it in an intelligent way, then again, I'm able to have each of the trials here, of the 8 trials here, I will find once, and I have each process parameter that is, each process setting that is also taken once. So I have something that, again, in terms of space filling of the whole space, is relatively well covering. Now, we're coming to what you were presenting and saying, and that's the only idea that I want to show you here, is what we are doing, in fact, which is a little bit different from what you were presenting in terms of this projection. So the projection that was initially taken was to say, okay, this triangle that you were showing before, in fact, from moving from the cube to this triangle, it's a very simple thing. You can really put this point exists already, becomes this one. This point exists, becomes this one. This point exists, becomes this one. This one is projected orthogonally on this red hyperspace and becomes this point here. This point here is projected orthogonally on this hyperspace, becomes this point here. This point here is projected orthogonally, is the center point, and that's the reason why I showed 2 center points. This point becomes also the one in the middle, becomes this point here. Very easy. The only thing, and this, we don't use the projection of Box and Howe, and that has been taken again by Cornell, that you were just presenting before, because doing that is extremely difficult to generalize. Whereas we do something super stupid, but allowing to be generalized to basically every problem. And everything is written here, but I just make an example. What we do is we start from the cube, which is this design here. Then we replace the 0 by the lower value, it was 0. The 1 by the higher value, which was 10 for each of these 3 sugars. And we end up with something with an intermediate design where we have 0, 0, 0. Oh, the sum is 0, the sum should be 10. Or 0, 10, 10. Oh, the sum is 20, the sum should be 10. So we have an issue. Then it's very simple. It's to say, oh, I have an issue here. It means I have 10 too much. The 10 too much I can take somewhere. I can take, not here, because already I'm at the lower bound. I have nothing. But I can take here, or I can take here. And we just take it proportionally to the range that we have, and that makes that basically the 0, 10, 10, where I have 10 too much, becomes a 0, 5, 5. Wow, super stupid. The cool thing is that in this situation, it gives us exactly that. And in a situation where it's much more complex, and I come again to what Michel was presenting, is to say sucrose was not between 0 and 10. Sucrose was between 0 and 5.4. Glucose between 3.4 and 8.5, fructose between 1.2 and 4.7, and the sum has to be 10. So my region is something that looks like this region here. And just applying exactly what we did before on this much more complex situation, we end up with something where we have this 8 points, because this again is a doubled point, where we can basically project always a cube in whatever restraint domain, and that's what I try to say here. It works for any type of constraint. We use that for multiple mixtures. We use that for nested mixtures, and always you just have to make a simple, stupid calculation. Now, if we look at how this competes with very often used designs, basically, because I would even say that what we call here the coverage design, which is already going into this direction, is a very nice design. We had naturally the optimal design here, where we have certainly no center point, yes. And we have here put in what that is our adjusted mixture design. What we have to try to become closer basically to the coverage design because we love them. And it's to say, we just make the whole region a little bit smaller, and at the end we come to things that are very, very similar. And if we compare, and this is just one example, but if we compare basically all the time our solution versus other type of designs, and we compare them on the efficiency and coverage efficiency, basically, you see for sure that the space filling design on coverage it is one, yes, because you cannot be better than it. But on the optimal design, you cannot be better than, for the efficiency, than a optimal design. But as you can see, a optimal design is not that good in coverage. A space filling design is not that good in optimal, and that's for sure, it's by nature. And we are somewhere in between. And that's where the cool thing is, we are nowhere the best, for sure. It cannot be because by nature we are not looking at that. But what we are looking at is to be good, consensually relatively good, and much more what we are looking is that we are not looking at only having this mixture, we are looking at having the mixture plus the process together in a very easy way. And I show you just an example here where we had really, it was in this project with Nestum. I come at the end very rapidly to what we really achieved, but we had the first phase with just 8 experiments starting from 2,7-4, where we were able to look at the main effects of 4 orthogonal factors, which was just replacing part of the wheat by 2 grams of grain 1, of grain 2, and of grain 3. And here it was really possibly not to go on a mixture, but to say just we replace part of the wheat. Then we had a humectant here, and then we had the sugars that had to sum up to 10%. After this, we were able to select what is the right thing to do here, and we were able to have a second step. And I just, before I tell you what this was exactly, what was behind this all, it's just to show you that we were here with something much more difficult, basically, where we had 5 components that had to sum up to 15 grams. All of them being, this one was between 2 and 5, this one was between 2 and 10, this one, so with very completely different constraints. And in terms of process, we had 4 different process factors, and we wanted to be in resolution 5, meaning we wanted to be main effects, but also 2 factor interactions that we wanted to have here, and using the old tables by our friend Adelman from 1962, we were able to have, just by again selecting the right columns of this orthogonal array, so that we were able to have this main effects and 2 factor interactions, and here the mixture part on a first order model. So combining everything in a very easy design, basically. So to conclude, basically what we tried to do is to have from this basic product here that was, again, very simplified, 80% of wheat, 20% of sucrose. We knew that perceived sweetness is a key liking driver. Our idea was to generate biscuity flavor, which is very congruent with perceived sweetness through Maillard reaction to reduce sugars. And this first step, with only 8 trials, we identified best combination of the grains in order to have free amino acids that can react with the best combination of sugars and the best humectant. The second part was, once we had that, we were able to generate this biscuity flavor. We had the second step was here to, on top of using the grains for having the amino acid source, that we have also an additional nutritional benefit. We were trying to move that up to 15%, and we had to fine-tune the process conditions, meaning that we were able to move from, in 24 trials, to move from something that had 80% wheat and 20% of sucrose to something that has 75% of wheat plus 15% of other grains plus 10% of sugar, so a nutritionally much more balanced product, and which is at the end even more liked by consumers. So we moved from this to this by just basically applying a very simple approach to merge factorial and mixture factors. And that's it.
Thank you very much, Andreas. Any questions, comment? Yes, please, Michel.
Thank you. Andreas, you talk about the efficiency, so that means you have a model. Which type of model you have?
Yes, here it's a very good
yes,
point.
Yes,
because
you are right.
here I was cheating a little bit. It was to say, because the example that I show is a first order model, and here I'm in a second order model. So here I'm in a second order model. It is exactly the one that you were showing. For the mixture, here on this calculations, here I'm on a second order model. Yes, absolutely. Yeah, for sure, absolutely. No, for sure. I'm here on the second. But exactly, and that's the reason why I say you are here absolutely the best naturally, and you cannot be the other for sure. It's logical. It's logical, I think, and that's exactly why it's always also to say which is the good design. It depends on which criterion, and I'm not sure that the one criterion is much better than the other. And that's the reason why I'm happy to be somewhere in between.
And when you mix the process and the mixture, which type of model do you have? An additive model for the
Yes.
mixture and the process?
Yes.